This video is entitled Limits at Infinity, which is a different topic than infinite limits that we've seen in a previous video. Limits at infinity means we are evaluating limits as x approaches either positive or negative infinity, not like infinite limits where the answer was infinity, negative or positive infinity. Now we're looking at approaching infinity. So kind of once again, there's several techniques that can be applied to this. So you can use pretty much whatever you like to come up with this answer, or depends on, if you're taking a class with a different instructor, someone watching this, that's always, what sometimes things that I say in videos doesn't mean that would apply to certain other classroom situations. But in my world, I'm open to whatever possible method to get the answer to these problems. Okie doke. So now let's say we have the function 2x over x minus 1. And we want to evaluate this as x goes to negative infinity and x goes to positive infinity. Let's see. Now, so notice I took negative 100 and I started decreasing it, negative 1,000, negative 10,000. So you see that x is getting smaller and smaller and smaller, heading toward negative infinity. And look at what the values of y are doing. They're getting very close to 2. So you can safely say here that that limit result is going to be 2. Now for positive infinity, went 100, 1,000, 10,000. Look at it coming that direction. Also heading towards 2. So you can say that that limit equals 2. Graphically, maybe I could have zoomed in on this a little bit better and added a little bit better graph of this. But anyway, it gets the point across. As you see, it's going to the left. It's kind of floating along that horizontal line right there, and which is at 2. And then same thing as you're heading to the right. That's what, graphically, we'll talk about something called horizontal asymptote here in just a second, but that ties in with these limits at infinity. We talked about vertical asymptotes in the infinite limit section. So this horizontal asymptote, the line y equals L, similar to vertical asymptotes. You may recall vertical asymptotes must say x equals something. Horizontal asymptotes must say y equals something, because that's the definition of horizontal line is all written as y equal. So y equals L will be a horizontal asymptote for the graph if the limit of f of x as x approaches negative infinity equals L, or if the limit as x approaches positive infinity of f of x equals L. If either of those are true. You can have some graphs that actually have a horizontal asymptote, but it only goes in one direction towards infinity, which is fine. That could be for a lot of reasons. The shape of the graph. But exponential functions are that way. We'll talk about it like e to the x later. I'll just kind of draw a rough sketch now, or I could bring it up in the calculator, I guess. Clear that, and e to the x, and I don't know what kind of window I have set up here. Oh, I got a weird one. So let me I'll just put a zoom standard here and see what it does. Well, you see that as it goes to the right, it's just rocket ship right up, toward positive infinity. No horizontal asymptote. But to the left, you see it's floating around toward the line y equals 0. So we can still consider that a horizontal asymptote. That's why the definition has or here and not and. meaning if either one of those is true, technically. Most of the time it's going to be where both of those are true, but I just want to show you that graph. That isn't a valid exception to that rule. So that one we just did has horizontal asymptote of y equals 2. All right, here's a little theorem on limits at infinity. This says r has to be a positive rational number. Rational meaning either integer or fraction. C being any real number. So c over x to the r, if it's a positive rational number, would go to 0. So basically a number over infinity raised to, is infinity raised to any positive exponent, whether it be a fraction or whatever, that's still considered infinity. In other words, the cube root of infinity is still considered infinity. So you basically have a large growing denominator while your numerator remains fixed. So therefore that fraction is going to get closer and closer to 0 as you go. Now this says, furthermore, if x to the r is defined when x is less than 0, then we have limit as x goes to negative infinity over c to the x to the r equals 0. Now that says if it's defined, that will be true. So where you could possibly run into an issue is, what if, like here, what if r was 1/2, which obviously would mean the square root of x? Well, then you couldn't put negative numbers in there, so that wouldn't apply. But if r was any positive integer, or even like 1/3, because you can take the cube root of a negative number and still be 0. So that's why it has that rule about being defined, because in case it ran in a situation where it wasn't defined. C over x to the r would be 0, but yeah, obviously with even roots mainly would be negative, would be undefined. So any odd fraction denominator, 1/3, 1/5, or any positive integer, it's going to go to 0. And so we got some right here. So that just means that's going to go to 0. 3 over x squared as x goes to infinity. Limit -5 over cube root of x equals 0. And this would be, here's an example of one, even though I have positive infinity, that would be okay if it was negative infinity, but not if it was a square root. And this one's okay, because raising it to a third power, you're okay. So that's a pretty easy rule. A number over infinity, limit-wise, is just going to go to 0. Over here, I threw one in right there, so you see negative infinity, I put a square root there, would be dne. But notice that when I put a cube root, though, it would still be 0. Yeah, so that's the whole issue about it being defined or not. Now this is, I made this little note here, obviously be careful to recognize what x is approaching when evaluating a limit. In a previous section, we learned this rule right here. The limit as x goes to 0 of sine of x over x equals 1. I remember doing a problem where x was approaching pi over 2, and I mentioned that's where you had to be careful, so you still have to be careful, obviously. Because sometimes people will just see sine of x over x and automatically think that's 1, but which is true as long as x approaches 0. But if it doesn't approach 0, then it won't be 1, it'll be something else. So this one is actually sine of x over x is going to be 0. Now it's kind of the concept of sine of infinity seems sort of weird. Now I use the squeeze theorem here to help sort of validate this a little bit. But if you think about it, see, sine is going to be just constantly, as you increase the x, it's just going to be somewhere between -1 and 1. It's always going to be a numerical value between -1 and 1. So no matter what it is, as long as x is going to infinity, then that's going to make it go to 0. But just to validate that further, this is a good use of the squeeze theorem. So if you agree that sine of x over x would always be between -1 over x and 1 over x, because sine is always between -1 and 1. All right. So in that case, we would know that this left limit, I may say left limit, I don't mean left hand limit, I mean the limit of this part right here, negative 1 over x goes to infinity, that would go to 0. The right side limit as x goes to infinity of 1 over x goes to 0. And since sine over x is squeezed in between those two functions, it would have to go to 0. So that's a real good use of the squeeze theorem. Or, you know, what I was kind of saying there about the numbers floating around there, but this is more precise. I like this. So, but it's clearly going to go to 0 because it's basically a constant over infinity. It's just a constant that floats around. You know, it's not a fixed constant, but it's still a constant. Now, I know some instructors that make their students do it this way. I don't, but I thought I would show one example in case you had to formally write this out at some point in time. But I'm going to show you a quicker and easier way to do this here in a second. Well, like I said, you can still use numerical techniques or graphing techniques. But this is sort of a formal algebraic technique where you divide each term by the largest powered term in the denominator, which is x squared. So you see I put every term over x squared and then simplified it. So 4x squared over x squared is 4, you have 5 over x squared, then you have 1, and you have 3 over x squared. Now, limits, they can all be evaluated individually. So you can take each limit and evaluate them individually. We've learned that the limit of a constant is always a constant, and that's true even with infinity. This is the first time we've had limit that goes to infinity, but the limit of a constant will be that constant no matter what x is approaching, even including infinity. So that makes that a 4. Now 5 over x squared, that's going to go to 0, and 1 will just stay 1, but 3 over x squared will be 0, and you get 4. So this one, the largest powered term, it's always based on the one in the denominator is x to the 4th. So I divide them all by x 4th. You see I simplified them. Like this one, I got 5 over x squared. Here, x 4th is 1. This gives me a 3 over x squared. Well, all of those, except for that one on bottom, all the other ones are going to go to 0. So you're left with a bunch of zeros, except for that one. 0 over 1 makes 0. So that limit would be 0. That's really a lot of work to come up with that when there's just really a simpler way to do this. And ironically, since these, infinity limits relate to horizontal asymptotes, this is sort of the way I teach this and would teach this in a college algebra class. Now, I would not use the limit notation in a college algebra class. I would probably just have, f of x equals that function, and we would be learning how to come up with, so we would only be learning this part on the right, the horizontal asymptotes. I wouldn't have any of this business here. But the same principle applies exactly like I would teach this in algebra. All you have to do is look at the largest exponent top and bottom and compare them. Because as you're going to either infinity or negative infinity, only the largest exponents in the top and bottom are going to dominate the entire function as you're going to infinity. That means all other functions all other terms are meaningless for infinity limits. They're completely meaningless. So if in your numerator, if you had like an x cubed plus x squared plus x plus 1, we only care about the x cubed. The smaller terms will not matter as you go to infinity. The dominant one takes over. That's why I have this plus dot dot, meaning all smaller terms. If those two exponents are the same, the limit will equal the ratio of the coefficients of a over b. And then, of course, horizontal asymptote would be y equals a over b. Once again, remember that the asymptote has to say y equals. The limit's just a numerical value. So this, go back up here. Like you see that example, and I'll go back to another one. So really this 4x squared plus 5 over x squared plus 3, you could get that limit really in about 2 seconds maximum. Because you see they're the same x squared, go 4 divided by 1 is 4. Same reason that, go way back up this very first example I showed you. Yeah, this one, 2x over x minus 1. The x's are the largest terms, 2 divided by 1. That guaranteed that limit was going to be 2, which therefore made the horizontal asymptote y equals 2. So that's we didn't ask for this one, but that the horizontal asymptote will then be y equals 4. Let's look at the next rule. If m is less than n, meaning we have a larger power on bottom than top, it's going to go to 0. Basically means that the fraction will get smaller because the denominator is so dominant, the whole thing will get closer and closer to 0. Never going to hit 0, but that's, remember, limits don't have to actually hit that target. They just have to be approaching it. So larger power on bottom, you don't even care about the coefficients. The limit will be 0, therefore the horizontal asymptote will be the x-axis, y equals 0. You see that happened right here. So this one could have done super quick. I could have said x squared on top, x squared 4 on bottom, automatically 0 is the answer. M is greater than n. We're going to have either negative infinity or infinity. Now these we're going to work out to determine which infinity it is. No horizontal asymptote. I will mention this. I'm not sure if this is going to come up anywhere or not. I don't put this on a test. This may come up in chapter 3 and the graphing stuff. We look at graphs of functions using calculus, but I'll just go ahead and tell you this now. If m is 1 degree higher than n, like third over squared or fourth over third, you have what's called an oblique, a slant asymptote. It means it would just be, horizontals are flat lines, verticals are obviously straight up and down lines, but a slant asymptote might look like that. And then the graph would kind of maybe, run beside it like this as you go to infinity, or run beside it like that way. But we'll look into that possibly later, but don't worry about that now. But the statement I still have here about being no horizontal asymptote, that's absolutely true. But then the limit's going to be either positive infinity or negative infinity. But that we want to see if we can come up with. We won't just use dn here. We'll actually come up with an infinity for this one. Because we're essentially approaching one direction, one infinity. You can't really approach, infinity can't really be approached from both sides, if you think about it. Like if you were x is approaching positive infinity, that's only one direction. You can't approach it from the other way. In other words, there is no such thing, even though if you've maybe heard of the phrase infinity plus 1, that's really not a thing. Even though you might think it is, it's not a thing. Alrighty. Let's see what we got here. Here's an example. I was talking about the slant asymptotes with power 1. So you have a slant asymptote coming along. Yeah, something like that. Right in there. Something like that. But we don't have the automatic, the easy answers, like the first 2 rules are the easy answers. Here we have to, it's easy to see there's no horizontal asymptote over here. That's easy, but that's to do the negative infinity or positive infinity, we have to do a little work. And the good news is you only have to work with the 2 largest power terms. That's it. Ignore everything else. So just drop everything other than the largest terms. So all I need is 2x cubed over 5x squared. So this one we're saying, what if it was approaching negative infinity? Okay, no problem. So we take 2x cubed over 5x squared. I pulled the 2/5 out, which is fine. I could have left it. But x cubed over x makes x. Well, if you then insert negative infinity, you have negative infinity in there. And the 2/5 won't make a difference. It'll still say negative infinity. Now, the only time those coefficients can make a difference is if it was a negative coefficient. Then it's going to change that will change the infinity. So if that had been negative 2/5, our answer actually would have been positive infinity. But if that coefficient's positive, then it won't affect anything. So that's going to be negative infinity. Now for positive infinity, okay, reduce it again, same thing. You put in positive infinity. 2/5 doesn't affect anything. You get positive infinity as the answer. All right, so let's look at the next example. All right, looks like I tried to get tricky here. I did this on purpose. Whenever you look at a rational function, do not always assume that it's written in the powers are in descending order. You may have to look for it a little bit. Obviously, I wouldn't make I wouldn't put like 15 terms in there. It wouldn't be that hard to find. But I'll put a little dot right here so you see. Actually, I put the largest terms here, and on the bottom it is the first term. So you see the 3x to the 4. So we got a little sneaky on you. Because if somebody wasn't careful, they might look at this and go, oh, 3 over x squared, it's going to be, 0, game over. No, that is not right. We have to work with 3x to the 4th over x squared, like so. Now let's try negative infinity. So 3x to the 4th over x squared as x approaches negative infinity. Bring the 3 out, x to the 4th over x squared. When you plug negative infinity in there, infinity squared is still infinity, but you are squaring that negative. That's very important. So you square that negative, so that then turns it to positive. Now our coefficient here is positive, so it'll stay positive. So that negative infinity squared will be positive infinity. And you see I've actually graphed this one. So you can actually see as it's heading both directions, it's going up to both infinities. So I guess, you could use the graph if you wanted to. That's fine. But I like to show it, analytically, because maybe somebody isn't using a graphing calculator. So, or actually, you could stick a big number in there too. Check it out. That big positive or big negative depends on which infinity. So you can kind of do this, numerically, graphically. This is what I would call the analytical way to do it. All right, so we come down here 3x squared. This time you plug positive infinity, so we'll still get positive infinity. So both these infinity limits this time turn out to be positive infinity. Now, let's take a look at this next one. So we can actually, property of limits allows us to split this up. So I can just treat the 5 by itself and then the rest of it. Now, if you look at this, you see there's an x on top and x squared on the bottom. And from our rules that we saw earlier, that means that limit's going to go to 0 because there's a larger power on bottom than the top. So that will go to 0, but the limit of 5 as x goes to infinity will remain 5. So we just have 5 minus 0, which will equal 5. Okay, let's take a look at this next example. Okay, they're out of order here. So the negative, now that's very, very important right here. Very important that we realize that minus goes with that 2x, because obviously if that, well, that's very important when infinity comes into play. Or actually it is, as long as for the other case where it's not 0, that's important. But I guess that it doesn't matter for this one because you have a larger power on bottom than top, so it's automatically going to 0. So if you go to 0, so if you miss the negative, that's okay. But my philosophy is, why not do it correctly? And here's a good example. So you have to include the negative right here. So actually, it's a minus 2x over a 3x, and same power, so it's a ratio of their coefficients. So it's negative 2/3. And then, of course, the horizontal asymptote would be y equals negative 2/3. All right. Now, we have a negative 2x squared over a 3x. So now we have a larger power on top than the bottom. So this is where we have to decide which infinity will be our answer. So negative 2x squared over 3x reduces x squared over x reduces to x. We have negative 2/3. So here's where that negative is going to be really, really important. See, when you plug infinity in there for x, that's going to be positive infinity. But the 2/3 doesn't really matter. The 2/3 itself doesn't matter. It's the fact that it's negative 2/3. The negative is what's key here. You can ignore the 2 and the 3 as long as you don't ignore the negative. So that one actually changes over to negative infinity. And just to show you, look what I did here. I did both of them, even though I was only asking for one of them. But look what happens up. Well, you can't see it. Well, there it is right there. There's what I typed in there. And when I put in positive 10,000, look at the answer it gives. It gives negative 6667. So it definitely is heading towards negative infinity. Excellent. Of course, no horizontal asymptote. So this is saying find the limit and then the horizontal asymptote, which I guess maybe I should have said, horizontal asymptote. That instruction probably should have said something like not trying to trick you here, but if any, because it doesn't have to have a horizontal asymptote. That's just a minor semantics issue there, I guess. But all right, how about this one? 3/2 on top, squared on bottom. That means you have larger on bottom, so it's going to be 0. So therefore, y equals 0 is the horizontal asymptote. Let's look at the next one. 3/2, 3/2. Those exponents match, so it's going to be 5/4. And then the horizontal asymptote will be y equals 5/4. So we have a 3/2 and a 1/2. Square root of x is to the 1/2. All right, so now that'll be 5/4, but what's the key here is x to the 3/2 divided by x to the 1/2. You subtract exponents, you'll get x. So now we have positive 5/4 there, a positive goes in infinity, infinity goes in, and infinity comes out, so it's positive infinity. All right, let's look at these These could be a little sneaky, especially when it's negative infinity. I've been known to sneak either one like this on a test, more positive infinity probably than negative infinity, but let's don't rule out the possibility that I might use negative infinity, so let's be real careful. But like I said, you could kind of use a large numerical value if you don't want to go through the process that I'm doing right here. If you're in my class, I think, this is kind of interesting. If you did kind of work this out. Now, once again, largest term top and bottom. Yeah, algebraically, it's not correct to split up a radical like that, but this is a totally different idea, like I've done right there. You can't do that algebraically, but it's because of the process of the limit heading towards infinity that we're allowed to do that, because we only care about the dominant term, which is the square root of 25x squared. Now, this is an interesting problem because if you look at this, and then now you take the square root of 25x squared, it would be real tempting to say that, oh, that's just 5x. And then 3x over 5x would just be 3/5. So the answer is going to be 3/5. But that's not true in this case. Because technically, if you want to be formal about it, which we will here, the square root of x squared really, by definition, is the absolute value of x. It's not really, it's x if x is positive, but it's not, it's negative x if x is less than 0, because that way it'll make sure it's positive, because that way if x is negative, negative of a negative will make it positive. Because yeah, the final result's going to be positive, but how that makes a difference here is if you write it then like this, you have x over absolute value of x, they don't automatically cancel, they actually cancel to -1, because you're now saying infinity over, well, I shouldn't say it that way because that's technically something in Cal 2 we're going to learn that's an indeterminate form. But if you just put a number in there, that's going to actually be -1. It's going to make it -3/5. Essentially, you can look at it as put negative infinity in there, makes it -3, and you have infinity over infinity, but it's -3/5. Now, if it's positive, that doesn't matter. You just get 3x over 5x, which is 3/5. But that's pretty tricky. You might think, no, there's no way that was right, what I just did on this last problem. You'll think there's no chance. But come over, look at my little calculator. Let me zoom in on this. Of course, the 3/5 might not have been that easy to interpret from this calculator output, but I'm just more important to show you whether it's negative or positive is the main thing. So you see, when I put in negative 10,000, look at that, it's negative 0.6. So I was right, it's negative 3/5. But then when you put in positive 10,000, it's positive 0.6, so that's that positive 3/5. So that is correct, but I could see where that could have caught a lot of people off guard there. Because it would have been tempting just to say 5x, 3x over 5x, which you can say when it's going to positive infinity. You can do that. That's okay. Pretty sneaky. So you can use a numerical value if you want to, if that bugs you, but that's okay too. But you just have to, break that square root down, and don't forget the square root, the number and the variable. You wouldn't want to mistakenly say the answer was 3 over 25 or something like that. So, all right, let's see if that comes up again. But that's something you definitely want to. I don't have any more here. I'm sure I have it. Practice problems or quiz or a review or something. So, yeah, that's very important. Because I have been known to put that on a test. All right, how about limit as x goes to infinity? Let's throw some more old trig stuff in there. See, trig's always fun. Cosine of 1 over x. All right, what kind of thought process will we go through here? Well, what I would do is I would put the infinity in there and take a look at what's going on inside the parentheses before I worried about the cosine part. Well, I put infinity in there. Limit-wise, 1 over infinity is going to go to 0. Then you just evaluate cosine of 0, which will get 1. That's all you have to do. So put the infinity on the inside first, get 0, and then cosine of 0 will be 1. Now, if you put infinity in a cosine, you just have it does not exist. Now, we saw that problem earlier where we had sine of x over x, and we're about to see that again right here. When you divide by x or something, then it's 0. But by itself, it does not exist because it's not really approaching anything as you go to infinity. It's just kind of, just picture it spinning around the unit circle, if you will, or something like that, where cosine is just constantly, it's not approaching anything, it's just changing value somewhere between -1 and 1. So that's why that would be a DNE. How about this one? X minus cos of x over x. We just split that up. And you have x over x. Cosine of x over x. X over x will just be 1. And then cosine of x, same thing as sine of x over x for the same exact reason. This one I typed in the Maple software to show you. That was 0. But the whole result's going to be 1, because it'll be 1 minus 0, so the final result will be 0, even though that limit by itself is 0. All right, here's just some sort of application type problem here. I wouldn't make a big deal out of this, so we'll just look at the couple of quick limits here. All right, let's see. Suppose the average typing speed after t weeks can be modeled by the equation. S equals 100 t squared over 65 plus t squared. So who knows, you might go into a line of work one day where you're doing some sort of mathematical modeling or something like that, where you're, not like you're, walking down as a runway model with math equations all over you. That means you're actually using data to create equations like this. Although the only issue that I have with this particular problem, as far as the reality of it is, I don't think you can come up with one model for each individual person. Let me finish this problem, and then I'll come back to what I was saying. But it's a real easy limit problem, though. That's the good news. So limiting typing speed means as t increases, gets farther and farther, do you reach a point where you've kind of hit your maximum? In other words, at what point are you going to be as good as you can do? So that means this. So limiting means as t goes to infinity. So you have 100 t squared over t squared, which means 100 words per minute. But I guess my issue with this particular equation is I don't think you can come up with one particular equation that's going to model everybody. I do believe that like this, whatever this is, particular person's referencing, that means they've reached their point where more time practicing, they're not going to get any faster than what they are. but that's probably not true for everybody. I mean, one person that's super skilled could do 100 words per minute, but there could be other people that no matter how much they work at it, maybe 50, 60 words per minute is the best they're going to be able to do. But I do believe in the idea that at some point you would improve until you couldn't get any faster. All right, here's just a quick little business example here. Cost equation for producing X units. Average cost is defined by C over X. You do not have to know that equation, C over X. If by some chance I were to ask this problem, I would absolutely give you this equation, C over X. So it wants to find the limit of C bar there. That's what they use for average cost in business classes, C bar, as X goes to infinity. So I take 0.5X plus 500 divided by X. And then we only have to work with the largest power, so it's 0.5X over X equals 0.5. That would be your average cost. Just real quickly, I'll tell you this is this equation consists of what's called a variable cost and a fixed cost. So let's say $500, a small business. Let's just say $500 was your startup. You had to pay, invest that no matter if you produce nothing. Let's say you spent that. But 0.5x is meaning you're spending 50 cents per unit to make whatever it is. Suppose that's the cost of the materials and whatever you're selling it for. That goes into revenue and profit. But anyway, but cost-wise, so this is saying as you do this over and over and over and over and over, lots and lots of times, as you do more and more, that fixed cost is eventually going to sort of like be buried in there to where, if it cost you $500 and then you've produced about 10 million, units of it, you've pretty much, that's probably excessive, but you've pretty much averaged out, so to speak, that fixed cost to where now it didn't hardly, account for much of the cost at all anymore. So, all right, well, that's your business lesson for the day. So with that being said, that ends the video for limits at infinity.